Hello and welcome back to another episode of Math with Son. Today we're going to be talking about a really important one, and that is connecting work to energy, specifically kinetic energy in this case. Now, kinetic energy is the energy of movement, and it is denoted by the formula K equals 1/2 mv squared, where m would be the mass and v would be the velocity. Okay, so kinetic energy, being the energy of movement, can be connected to work because work is done when we had a force acting times a distance. So originally it was force times distance, that was equal to our work. Okay? And we talked about work in terms of friction. Well, friction acted against us, and that was work done against us. Well, if you think of friction and you think of kinetic energy can also represent kind of like heat and movement and all sorts of other things. If you are converting energy in some way, work had to be done. So I'm going to say that again. If you convert energy in some way, work had to be accomplished in some way, shape, or form. So another way to think of work is the change in kinetic energy. Okay, so work can be the change in kinetic energy. Work transfers energy from one object to another. So with that in mind, you can also think of work as, knowing our kinetic energy formula is 1/2 mv squared. Change in kinetic energy would just be how far apart they are or the difference between them. So you could take your 1/2 mv final squared and just subtract your 1/2 mv initial squared. So however fast you were going at the end, take that away from how fast you were going at the beginning, and you would end up with your overall work formula. Okay, so let's do a few examples with this because they have a lot of benefit. It connects things that allows you to find the force when you only have the velocity, or vice versa. So a 15 kilogram mass has a speed changing from 10 meters per second to 30 meters per second in 8 seconds by a constant force. Okay, so let's find out the work that this gained, because it went from a slow speed to a faster speed, or a slow velocity to a faster velocity. So we are going to use 1/2 mv final squared minus 1/2 mv I squared for initial. So this would be 1/2 the mass, which is 15 kilograms, times the velocity, 10 meters per second squared, minus 1/2 final would be 30. It ended at 30, minus 1/2 15 times 10 meters per second squared. And if you do that math, you would end up with a change in kinetic energy of 6,000 joules. Okay? So that tells us that we have gained 6,000. If you flip-flop it, by the way, you would actually have lost 6,000. So make sure you're doing it in the right order, because if you're going faster, you're gaining in energy, not losing in energy. What is the force of magnitude of the force? Well, KE delta K is equal to work done. And remember from last video, work is equal to your force times your distance. Okay. Well, we got some of this aspect for us. We got 6,000 joules is equal to our force. So that would indicate, 6,000 joules is equal to our work. If we solve for force, we would be dividing by D, and we would get our force is equal to W over D. Now, if we know that the work is 6,000, we just have to do 6,000 divided by the distance. So what is said distance? Well, that requires even more work because we don't know the distance yet. We know our initial velocity, we know our final velocity, and we have our time. So we have to use, yet again, another kinematic formula. Our kinematic formula this time would be D is equal to VI plus VF divided by 2. Times time. So you essentially average the velocities, you add them together, you divide by 2 and multiply by time, and then you would be able to figure out the distance. So if we do that, we would have D is equal to VI, which is 10, plus 30 for VF, divided by 2, times our time of 8, and we get 40 divided by 2, which is 20, times 8 gives us a distance of 160 meters. So now that we know our distance, we can plug that in, 160, and we can figure out the overall force that was done on here was equal to 37.5 newtons. Okay? Next one. All right. So here, we got a textbook. It's sliding across the classroom floor. It initially is traveling at 6 meters per second, so that would be our VI. And the coefficient of friction sliding between the books is 0.15. Find the distance required for the book to stop. Now that actually has two things. That has your question. We want to find the distance required for the book to stop. But also, if it stopped, that means we want our final velocity to equal 0 meters per second. All right? So with that in mind, again, work is equal to the change in kinetic energy. Well, we have our VF, we have our VI. We don't have the mass. So let's see how that would work out. We got 1/2 mVF squared minus 1/2 mVI squared. That would be the change in overall kinetic energy. But it also would be essentially needing to equal the coefficient of friction, like how much the force of friction is doing. Why? Because if we subtracted our final velocity and the overall kinetic energy, all of that was put into the friction. All of that was put into friction. Okay? And if that's the case, then we would know that 1/2 mVF squared minus 1/2 mVI squared, the coefficient of friction, and how we find that friction force would be the coefficient of friction, negative coefficient of friction, mgd. Okay? So what's going to cancel out here? Remember how I said we got an issue, we don't have mass. Well, we got mass canceling with mass canceling with mass canceling. All the masses would cancel out. What else do we know? Well, we also know that the final velocity is 0. So this is essentially going to be, even if the m didn't cancel out, that would be 0 times 1/2 is 0. So we have negative 1/2 times our VI squared, which would be 6 meters per second squared, would have to equal the coefficient of friction times gravity times distance. Well, we're looking for distance. So what is the coefficient of friction? That'd be negative 0.15 times gravity. That would be 9.8. Or we could go for 10. I'm going to go with 9.8 times distance. If we solve for distance, we would just be dividing by the negative 0.15. Oh boy, negative 0.15 and the 9.8. All right, so let's do that. If we do that, we end up with 36 times 0.5 divided by 0.15 divided by 9.8. You end up with a distance of 12.24 meters. Ta-da. All right. We got one more for today. This one's an easy one, and it's more of a review of what we did before. Remember that force is equal, work is equal to force times distance. Well, here, if it were a rectangular shape, you could just do 8 times 5 and you'd get 40. But it's a triangular shape, which indicates that the force was increasing. Therefore, the work being done per meter would also be increasing. So in order to find the total work done, you have to find the area underneath the line or the curve. Okay, so for those of you in calculus, you would be taking the integral. But for those of you that have not taken calculus, you can find that your overall work is force times distance. But in this case, we would have to just find the area of the triangle. So we would have 5 for our distance, and our force is changing. It started with 0, it ended at 8. You could also think of it as averaging the difference between 0 and 8, which is 1/2, 8 times 5, or better known as the area triangle of a triangle, 1/2 base times height. So if we do 1/2 times 8 times 5, we end up with 4 times 5. We would find out the total work being done would be 20 joules. But it doesn't want us to know all of that. It actually wants to know what is the speed of the object at 5 meters. Okay, what do we need to do for that? In order to figure out that, we would need to know that the area is equal to force times distance, but the area is also equal to the change in kinetic energy. Well, if the change in kinetic energy is equal to 20 joules, and we know our initial and final velocities, which we could figure out potentially, then we should be able to do this. So let's think about this. We got 1/2 mv f squared minus 1/2 mvi squared. That would have to equal 20. Not only that, but your initial velocity was 0. That's just whoop, gone. So if we wanted to know what is the final speed at that point, we would need to just plug in the 0.4. We got Vf squared would equal 20. Multiply by 2, divide by 0.4, 20. Multiplied by 2, and then divided by 0.4. You get Vf squared is equal to 100, and that means your final velocity would be 10 meters per second. All right, that's going to do it for this one. Until next time, stay positive, my friends. We get to talk about gravitational potential energy and the conversion between potential energy and kinetic energy in the next one. I will see y'all then. Bye.